Modern medicine approaches the human body as a complex biochemical reactor. We measure hormone levels, track protein synthesis, and attempt to balance molecular equations. But chemical reactions occur within a physical housing. These molecules are pumped through pressurized pipes, suspended from load-bearing columns, and subjected to constant gravitational stress. Biological systems are bound by the macroscopic laws of classical mechanics, structural engineering, and thermodynamics. Every breath, heartbeat, and movement requires measurable physical work. When a joint degrades or an artery ruptures, it is the end result of a deterministic mechanical failure, governed by the same physical forces that tear down bridges and burst industrial pipes. By mapping physiological systems to the math of fluid dynamics, solid mechanics, and thermodynamics, we can measure human biology with structural precision. Evaluating physiological function as an engineering problem allows us to define the specific physical limits of human health. When we calculate the physical tolerances of the machine, we can identify exactly why it breaks. Consider the cardiovascular system. Instead of viewing the pulse solely as a biological rhythm, we can evaluate blood flow as a continuous fluid mechanics problem. The movement of fluid through the body's vascular network is governed by the Hagen-Poiseuille law, which determines volumetric flow rate. This diagram maps the formula over the vascular network. It calculates flow rate, Q, by factoring in the pressure gradient, the length of the vessel, and the fluid's viscosity. The critical variable in this system is the radius of the vessel itself, represented by R. In the equation, the radius is raised to the fourth power. This introduces a nonlinear weight to the system, meaning the overall flow rate is entirely subordinate to the width of the pipe. If microscopic plaque reduces the radius of a vessel by just 16%, the mathematical output dictates that volumetric flow rate will be cut in half. A fractional reduction in width triggers an exponential drop in the volume of liquid that can pass through. In a human patient, this drop in flow leads to downstream oxygen starvation. When the volumetric flow fails to meet the metabolic requirements of neural tissue, the physical conditions for a stroke are met. A stroke is the physical manifestation of a system violating its own mathematical flow requirements. The risk compounds rapidly, dictated by the physical geometry of the vessel. This mechanical logic applies directly to the aerodynamics of the respiratory tract. The flow of air through the throat is defined by Bernoulli's principle, which establishes an inverse relationship between the velocity of a fluid and its static lateral pressure. This cross-section of an airway illustrates the aerodynamic challenge. If the airway narrows due to muscle relaxation or tissue obstruction, the specific volume of air required for each breath is forced through a tighter physical space. To maintain the required volume output through a stricture, the air must accelerate. The velocity variable, v, sharply increases as it passes through the biological choke point. Bernoulli's principle dictates that as velocity goes up, lateral wall pressure must go down. This drop in outward pressure generates a measurable mechanical suction against the surrounding tissue. The vacuum created by the accelerating air pulls the walls of the throat inward. This suction forces the tissue to pinch completely shut, an event clinically diagnosed as obstructive sleep apnea. Tissue collapse in the airway is a fluid dynamics inevitability, dictated by velocity, rather than an inherent biological weakness of the throat muscles. Moving from fluid mechanics to solid structural engineering, we can evaluate the human spine. Mechanically, it functions as a rigid vertical structural column. Medical models often focus on isolated muscle weakness or joint health when discussing postural failure and spinal compression, but a spine under gravitational stress obeys Euler's critical load equation. This wireframe model displays the structural formula used to calculate exactly when a load-bearing column will buckle. The formula determines the absolute maximum force the spine can sustain, FCR, by dividing the material stiffness of the bone by the squared length of the column. The moment the applied downward vertical load exceeds the critical force threshold, the structure can no longer maintain its linear shape. It instantly yields to the stress. This structural buckling manifests as slipped discs and herniations. The vertebrae are pushed out of alignment by sheer mechanical overload. The same structural mathematics used to calculate bridge failure define the physical limits of the human spine. Zooming in from the macroscopic column of the spine, The internal structure of a bone like the femur reveals an organized microscopic crystalline matrix. Bone remodeling is often described as a biochemical process, driven by hormones and calcium levels. However, the physical crystal structure of bone material possesses an inherent electromechanical property known as piezoelectricity. When mechanical stress is applied to the bone, the physical deformation of the lattice generates a distinct electrical polarization across the tissue. This electrical charge acts as a computational blueprint. It guides osteoblast cells, directing them where to deposit new minerals to reinforce the structure against the applied load. When physical stress is removed, such as in prolonged bed rest, the electrical signaling halts. Without the piezoelectrical data instructing the cells to rebuild, bone density degrades. Skeletal growth is an active, computed response to physical pressure, translating mechanical stress into electrical data. At the deepest, microscopic cellular level, we find that biological cells operate precisely like complex thermodynamic engines. Biological states, such as the metabolic shift during fasting, are driven by entropy and energy gradients. This energy landscape graph maps the cellular state. We can track how cells alter their behavior under stress using the Landau phase transition free energy model. The model hinges on a critical threshold variable, TC, which represents the point where environmental stress forces the system to abandon its current state. Biological cells do not gradually fade from one behavior pattern to another. They maintain operational stability right up until they hit this critical threshold. The moment the cellular environment crosses the TC boundary, the cell snaps into an entirely new physical configuration to survive. This thermodynamic mechanism is what forces a cell to switch from an active growth state into a defensive posture of repair and autophagy. Cellular transformations follow the energy gradient, resulting in abrupt, calculable thermodynamic phase transitions. Scaling out from the individual cell, this CAD model of human anatomy reveals a system governed by absolute mathematical operators. When translated into the language of fluid mechanics, structural loads, and thermodynamics, these biological systems become measurable and predictable. Physiological outcomes in these mechanical systems follow deterministic physical laws. They respond to pressure, load, and energy transfer with mathematical consistency. Evaluating the human body as an advanced mechanical engineering system provides a rigorous framework to predict when the machine will reach its physical limits.